بسم الله الرحمن الرحيم. Assalamu alaikum wa rahmatullahi wa barakatuh. Today we're going to continue talking about logarithmic functions part 2. Now let's talk about the third part, which is inequalities of logarithmic functions. A and B are two strictly positive real numbers. Len A is greater than len B if and only if A is greater than B. Len A is greater than or equal to len B if and only if A is greater than or equal to B, and similarly for smaller and smaller than or equal. Solve each of the inequalities below. Now here we have to pay attention to something very important. Let's see. First, if we apply property 2, we get x is greater than 2x minus 2. So minus x is greater than minus 2, x is smaller than 2. But this would not be the answer because we have to take the intersection between this answer and the domain of definition. Or x should be less than 2 providing that x is greater than 1. Now we have x is greater than 1 from the domain of definition and x is smaller than 2 from the inequality. So if x is greater than 1 and smaller than 2, the answer would be x is between 1 and 2. Then x is smaller than or equal to 2 for this condition. So again, pay attention, we solve the inequality and then we find the intersection of the solution with the domain of definition. Here, we can say that x is smaller than or equal to e squared, and we know that x is greater than 0, so the intersection would be x is between 0 and e squared, including e squared. Now, this inequality, remember, again and again, to solve an inequality which is not of degree 1, we compare to 0, factorize, we find the roots, we draw a sign table, and we find the result. This is the domain of definition. So here it is already compared to 0 and it cannot be factorized anymore. We begin by finding the roots. If len x minus 1 is 0, this means that x is e because len x is 1. And if 6 minus 3 len x is never 0, so x is never e squared. So in fact, we have e and e squared. We draw the sign table. This is e squared, remember, in increasing order. And we have the domain of definition. We have to put an impossible at 0. So len x minus 1 is 0 when x is e. This is e. Now, how do we fill in the signs? In fact, we deal with len x as if we are working with x. So we apply opposite, same. Opposite, same. Again here, this expression is 0 when x is e squared, and we deal with it as if we have x, so it will be positive, negative, and the final answer is, we have a 0 here and impossible here. From the domain of definition or from this condition, we have minus, plus, minus. Now we need the answer to be positive or 0, so the answer would be, in this case, e squared, including e and excluding e squared. So this is the list: equal, greater, smaller. Solve each of the inequalities below. Try to solve the first inequality alone. Pay attention to its form. So if we eliminate len, we get 2x greater than 2 or x is greater than 1. Remember, we have to find the intersection between this answer and the domain of definition. X is between 0 and 2 and it's greater than 1. So it will be x is between 1 and 2. The second inequality. So try to isolate len x. We get len x is smaller than 3, so x is smaller than e cubed. and it's already greater than 0, so we will get x is between 0 and e cubed. Now this inequality, try to do it alone. Well, this is a product, we have to find the roots. The first root is x equals e, the second root is x equals e to the power 4, table e power 4, and the domain, which is 0 plus infinity, excluding 0. The first factor is 0 when x is e. Signs, we have opposite same. The second factor is 0 when x is e to the power 4, and signs also opposite same. We deal with ln x as if it were an x. Now this is a 0, this is another 0, and then we have plus, minus, plus the product. We need the answer to be greater than or equal to 0, and x will belong to 0, e union e to the power 4 plus infinity. Now this is a miscellaneous question. F and g are two functions defined as follows. This is f, this is g. C and G are their curves. The question is to study the relative positions of C and G. Remember, to study the relative positions of two curves, we find the difference between the two functions. If the difference is negative, you can say that C is below G. If it's 0, we say that C cuts G. And if it's positive, we say that C is above G. Try to do it alone. Now, f of x minus g of x, if we just replace, we get ln x quantity squared minus 2 ln x minus 3, and we need now to study the sign of this expression. The roots are ln x is negative 1 or ln x is 3, so x is e to the power negative 1 or x is e to the power 3. We draw the sign table. Remember, x can never be 0. It's defined on 0 plus infinity. Now this is f of x minus g of x. It plays the role of x, so we have to put a 0 here, a 0 there, same, opposite, same. Now positive means c is above g, negative c is below g, and positive c is above g. The difference is 0, so c cuts g. The difference is 0, c cuts g. Now the 2 points of intersection are e to the power negative 1, 1, and e to the power 3, 9. Rima, Amir, or Mira. We need to solve this inequality. How did Rima solve the inequality? She compared to 0. She took ln x as a common factor. Then she said that ln x is less than 0 or ln x minus 2 is less than 0. So each factor is less than 0. She continued, x is smaller than e to the power 0 or ln x is smaller than 2. In other words, x is smaller than 1 or x is smaller than e squared. Thus, x is smaller than 1. Amir compared also to 0. He took ln x as a common factor. Then he found the roots. X is 1 and x is e squared. He drew a sign table. This is a 0, this is another 0. The domain 0 plus infinity, shading part, same, opposite, same. And he put the answer x belongs to 1 e squared because we need it to be negative. Mira cancelled ln x and ln x. What remains? Ln x is smaller than 2, so x is smaller than e squared. Now x is greater than 0 from the domain of definition, and x is smaller than e squared. This means that x is between 0 and e squared. Now, which method is correct, which method is not? I think Amir's method is the correct one. Pay attention, we cannot eliminate in case we have an x, especially when we have inequalities and the first one is totally wrong.